Hi viewers and students, welcome to today's class on redox titration. So in today's video, we are going to be standardizing or carrying out a titration between a solution of KMnO4, which is an which is an oxidizing what agent with what ion 2 tetraoxosulfate 6, which is what a reducing agent. Okay, just like your acid-base titration, but this titration is quite different from your usual acid and base. Though in this titration, potassium permanganate, that is KMnO4, will be acting as acid, while ion 2 sulfates will now act as what? Base. So in this titration, the A, which is the KMnO4, this one is going to assume A. So A is this, and then B is what? This. So the one we're going to put in the burette, this is burette, clamped on a retort what? Stand. And you must stand vertically, and your eye level should be on the meniscus. And then in this titration, just like in acid-base titration, acid is poured into the burettes, and then the base is pipetted and then transferred into the what? Conical flask or a Lemaye's flask. But in this titration, the solution we're going to pour in here is the solution of what? The KMnO4. And the one we are going to be pipetting is what? Is the ion 2 what? Sulfates. Using this piece of apparatus, which is a what? You're transferring what? Pipettes. Now, before the titration, as a student, you are expected to read the question, understand the question and digest it before you start to perform the experiment. First of all, every school use a uniform volume of these pipettes. Sometimes it varies in different sizes. So depending on the school, in this video, we're going to be using a 25 centimeter cube volume of pipettes. So these are the information you have to provide. The examiners must be aware that the pipettes used in this titration is what? Recorded, and in 2 decimal places. So here, we first write what? Volume of pipettes. Pipettes used is what? This is what? 25.00 centimeter cube. Are you there? And then in this titration, it does look like there is no indicator. Yes, there is no indicator, but in this case, indicator use. There is one solution here that performs 2 functions in this titration. One is the solution that is going to be here, which is the KMnO4. It's going to act as oxidizing what? Agent. And at the same time as what? Indicator. So the indicator is what? Is what? Self. That is itself. Okay? Or the indicator is what? KMnO4, or it can also be referred to as what? Titrants. So any of this can go. And then color change at endpoints. Okay? As far as this titration is concerned, the color change at the endpoints, what will mark the end of the reaction is the color change, which is what? Which is pink. So these are the information you must provide before your table of value. Before you start the experiments, at least you should put this thing down. Okay, let's say that this is going to be your first experiment, second experiment, and then third experiment. Okay, now make sure that you don't forget to insert the units for the volume of what? The solution A, which is K-4. And then you have your final reading. Your initial reading follows suit. And then volume of, don't say acid, because it's not an acid. Say volume of what? A what? Use. Okay, you are the one that will now provide the values as you carry out the what? Experiments. You have to run the experiment 3 times to ensure you obtain consistent what? Titer value. So in this video, you're going to watch me as I perform the experiments and then insert my value obtained from the bullets. This is the bullets. So you see, an exam body like WAEC will give you a question that will follow up the practical. They will tell you that A is a solution of maybe 0.0100 mole per dmq of KMnO4. You come up with this kind of question. That's the information you need about the titrants. Then next is going to be what? B is a solution of FeSO4, maybe the one with water of crystallization. Okay? Then maybe this time whose concentration is unknown. Okay. Then you are now to put solution A into the burettes and then titrate it against 20.0 centimeter cube or 25.0 centimeter cube portion of solution B, comma, add 10 cm cube of dilute H2SO4 to acidify solution B before titration. And then, so you're going to follow what you see here and perform the experiment. So you have to perform the experiment how many times? 3 times. And then ensure that your results are what? Consistent. So they say in the question we should pour A into the burettes. So this is the burettes. This is how we pour A. Solution A is KMnO4, whose color in solution is what? Intense to what? Purple. So you add it gradually or step by step. Okay. After putting or pouring the solution A into the burettes, please ensure to what? Remove the what? Funnel. This will be one of the precautions taken to ensure that your results are accurate. That after pouring after pouring solution A into the burette, that you remove your what? Funnel to avoid drop. This drop could mistakenly add to the volume that you've already taken, and that will affect your volume. So what do? You remove the volume, then adjust the solution in here to obtain your what? Initial what? Reading. This initial reading will come before the final reading, because the final reading is a reading that's the reading that you obtain during the course of the reaction. But before the reaction starts, this is initial reading. So we set it up to take the reading and make sure that the meniscus is within your eye level to avoid a parallax what? Error. So I will adjust little bits. And in this titration, because of the intensity of the color of KMNO4, it will opaque lights, and they will not allow lights. It will not allow light to pass through, so it's not going to be visible, that is visible for you to take your initial reading from the lower meniscus. So this is one titration that you read from the what? Upper, not what? Lower. Because the lower meniscus is very difficult here to see, because this color here is what? Opaquing what? Light. So it's not going to allow light, and you cannot see if light does not enter. So this is what you do. So you try to read both your final and initial reading from where? Upper what? Meniscus. So the upper meniscus here, I think I can see something like 1. So I have my initial reading here as what? 1. Make sure it's in 2 decimal what? Places, which is what? 1.0. Are you with me? Okay. You have taken care of this. Then the volume of the titrant, or A, for now is unknown. But the volume of the analytes, which is the ion 2, is going to be known, because they're going to pipette. Already the volume of this is designed as what? 25. WAEC will always give instruction against 20 or 25. So you cannot use the 2 volumes. So that's why you are recording your volume before the commencement of the table or experiments. So the examiner will now know the actual volume you are using for the titration. Failure to do so, the person marking the script will not know the setting volume, because the volume will appear to be either 20 or 25. So that you have to state. So for this video, we are using 25 as our what? Volume of what? Pipette. And that is going to be, by extension, that will be the volume of our what? B. So when we are going to be solving numericals, this will assume our volume of what? B. So you now take the value, or by what? Measure the value by what? Pipetting. Pipetting here is what? Sucking it until you reach this what? This mark. But during the course of transferring it from your mouth to the hand, you have to have the volume kind of what? Exceed the mark. There is a mark on this pipette. So you use this way, and be very careful not to allow the solution to get into your mouth. It's very important. Okay, it's an unstable compound, and it's very hazardous. So make sure you keep enough water, because of what? Fear of what? Mistakenly what? Sucking the what? Base. Okay. So I was very careful not to allow it to get close to the mouth. So this is what you have. So you gently release air inside so that you can adjust till you get to that mark. I think it is on it. Immediately you transfer. And during the point of transfer, don't allow the pipettes to what? To touch with the neck or mouth of the conical flask. Just gentle allow it to discharge. And then upon discharging, you are not to blow the last drop. It is not designed to enter here. And that is also going to form part of your precaution. That you ensure that you do not blow the what? Last what? Drop. If you blow the last drop here, that means it's going to affect the volume which you have already stated to be what? 25. Maybe it's going to be 25 point something. So it's designed not to allow. Don't say my solution is still remaining and then you now blow inside. So it will spoil your results. Take note. That will form your part of your precautions. Now, don't start titrating if you do not acidify. Because the principle of this titration is very simple. Very simple. You are titrating an oxidizing agent of MnO4 minus, okay, a substance with 4 bonded to 4 atoms of oxygen. Okay, is a powerful oxidizing agent. And then you are now titrating with ion 2. Some will wonder why are we not using how it is in the how it is stated, KMnO4. In redox reaction, potassium is a spectator ion. And in this reaction, any species that is not actively involved in the reaction is what? Is removed from the ionic equation. And so, in balancing the equation, there is no need keeping that particular ion, since its oxidation states in the reaction will not what? Change. It will remain fixed. Same thing with ion 2 sulfate. The sulfate in that ion 2 is also what? A spectator. So what you have now is what? Ion 2. Now the reason why this is an oxidizing agent that in the course of the reaction, it reduced from 7 to what? To its lowest oxidation state of what? +2. That is having lost this oxygen atom. So in this very reaction, you must add a proton from an acid that combine with the oxygen to produce water. And upon the acid you add, there are 3 lists of acid that could be added: HCl, HNO3, or H2SO4. We're not going to use this as an acid that can furnish this reaction with proton, because this acid is an oxidizing acid and it's going to interfere with the reaction. We're not also going to use this HCl because in this reaction, potassium permanganate here will oxidize chlorine and then produce chlorine gas. And that will also interfere with the reaction. And then H2SO4 is the better choice. Why? Sulfur is not going to be oxidized. And then the hydrogen will now furnish enough hydrogen ion that will what? Acidify this solution. Or the hydrogen ion that will combine with oxygen, with this oxygen here, to produce how many molecules of water here? You now check how many oxygen you have here. How many do you have here? 4. So 4 go here. So how many moles of hydrogen ion from acid do you have to add here to balance what you have there? Is what? 8 what? H plus. Are you with me now? So it does look like the ions in this reaction is balanced. You have 8 H here as against 8 hydrogen on the other side of the equation. You have 1 Mn here, 1 Mn, 1 Fe. Okay, Fe in the reaction also need to be oxidized. Since this is reduced, this is going to what? Oxidize to what? To what? Ion 3. So it's being added in the reaction as well. Okay, let's check if it's balanced. 8H, 8 balance, Mn is 1, Mn is 1, O is 4, O is somehow 4 here, ion is 1 here. But on the charge, on the basis of the charges, it's not balanced. This is 8. Of course, 8 minus 1 will give you 7. 7 plus 2 will give you what? 9. So total net charge here is how many? 9. So let's check if we can have 9 here. This is what? 2. So the only charge here is this 2 and this 3, which is total of how many here? 5. But let's now balance the charges. On how to balance the charges, we're going to collect stems, ions that are very, very alike here. You notice that this is very, very much alike with this one. Are you with me? And the difference in the charge on both sides is what? Is 1. So write that one here. 1 E minus. We're also going to do the same thing. This one and this one are almost what? Similar words, ions, isn't it? Similar things are there. The oxygen here is what has produced this and this as well. So now, let's check. So we are not going to be considering this again now. So this and this has been taken care of. Now let's check charge that is produced from here to here, including this, and then this, and then this. Well, let's go. This is what? 8, isn't it? 8 minus 1. 7. That is the number of charges you have on this side. On this side, how many do you have here? How many do you have here? 2. How many do you have in water? 0. Shey, water is neutral. So 2 plus 0 is 2. So you have total net charge of 4. How many here? How many here? 7. Total net charge here is what? 2. What is the difference on both sides? What's different there? 5. So here will become what? 5 E what? Minus. So as you produce 1 from here, you produce 5 from here. So what you produce from here, use it on this. You produce 1, so 1 multiply this will give you 1. 1 multiply this will give you the same thing. 1 multiply this gives you the same thing. 1 multiply water gives you the same thing. Then 5 multiply this gives you what? 5. 5 multiply this gives you what? 5. At this point, this equation is balanced. Let us check if we are correct. How many H is here? 8. How many H is here? 4 times 2 is 8. Mn is 1, Mn is 1. O is 4, O is 4. Fe is 5. Fe is also 5. Let's check the charge. As of that one, we check the charge is not balanced. Let's check if this one will balance. This is 8, Abi. That is plus 1 times 8 is plus 8. Plus 8 minus 1 is 7, isn't it? Just keep that 7 aside. 5 times 2 is 10, isn't it? 10 plus that 7 is how many now? 17. Let's see if we can have 17 on this side. This is 2, isn't it? So this is 2. This is 0. So 2 plus 0 is 2. Let's keep that 2 aside. We have 3 times 5 is what? 15. Then 15 plus 2 is what? 17. So on this case, this equation is what? Balance. So now, in this table, in this practical, we are going to acidify the solution before we start titrating. So on acidifying, you may be asked to measure 10 ml of acidified H2SO4. So this is my acidified H2SO4, just 10 ml. I think this should be enough to give me 10 ml. Okay, this is somehow 10 ml. Look at how you acidify. You put inside. That is the H plus you've added to the ion 2. Then you now start mixing. Who can tell me the color of manganese 2? Manganese 2 is colorless. Is what? Colorless. So if you now see, what is this? Manganese 7, isn't it? So that means if it goes in here, let's see. If it goes in here, what do you see? You see the purple go in and then turn colorless, isn't it? At that point, it is being reduced. Who is reducing that manganese 7? Ion 2. Because ion 2 is what you have here. So as I'm titrating this now, going in here, it is being reduced. Turning to what? Colorless. I'll keep titrating. I'll keep titrating until reaction what? Occur. So let's see if reaction will occur. Has it changed? Now, who can tell me? Okay, now, in this titration, the reason why the color persists, that it doesn't turn colorless, is because all the ion 2 in the conical flags has been what? Used up. So any little amount of hang like that. If you have SS, wrong reading. If it doesn't give you a color, yes, it will still give you color, but the color will be overshooting. You overshoot the color. The color will be changing upon oxidation. But this is the actual color we have. Okay, I should continue. Now, the reason why the pink persists, the reason the oxidants or the titrants is referred as indicator because it indicated itself in the reaction by showing its what? Color. Reason why the color is not purple in this solution is because of the concentration of the amount of this that is in here. The amount of manganese that is in here is not as that is in the what? In the borate. So as manganese 7 goes into this particular piece of apparatus, it turns colorless until all the ion 2 in the reaction, in the Elimias flags is used up. And then no other ion 2 in the solution. Then itself now will be what? Indicated. And that is the end what? Point. Now, at this point, you now read the what? You now read your burette. And that will be your final reading for this experiment. I think I have 28.00. 28.00. So how will I get my average volume of AUs? I'll subtract. This is going to give me what? 27.00. Are you with me now? I don't think this will be enough to run the next titration. So what do you do in this case? You fill the what? The burette again. So we refill. Zero 0.50. You rinse with your distilled water. You run the experiments again, the second time. You transfer. Ensure you don't blow the last drop. Acidify. Then start again. Second titration or second experiment. Now I have an idea the endpoints. So once I get to the endpoints value, I will ease the titration. Is when I get up to 25, I will start using drop, drop, drop. So I will now know when one drop exactly change that. So you know it's about to change now, Abi? Okay. Just watch the video. You will see as it changes gradually. I think it's changed. You stop titrating. Okay. So the first one we did is actually going to be our rough. Because okay, this is exactly 24. So I have this as 24.00. So what do you have here? What do you have here now? 23 point what? Point what? 5 what? 0. Okay. So we refill. But to be very fast because you're under exam condition. Don't forget to rinse with distilled water. Okay. This last titration, you'll be very careful so that the two will be consistent. Okay. To avoid any case of using the last final as initial, please you refill. Refill. Okay, I think I'm on 1 point. Okay, 1.00. Okay, we start the last one. Have I acidified? No. You acidify. And then you start titrating. until you know when one drop exactly changes. Okay. Okay, I think if this happens, you repeat the titration. You acidify. Okay. Okay, so got 24.30. So what do you have here? 23.3 what? 0. Okay. So this one is off. What do you do? You cancel. It's not cancel, just to show the examiner that this is what? This is not consistent with these two readings. Okay, so you're going to use what and what as your average. So what is going to be your average? So your average title now will be what? Average volume of A used. So we use what? Experiment what? 2, Abi? Plus experiment what? 3 divided by what? 2, which is what? 23.50 plus 23.30 divided by what? 2, which is what? 23 point what? Point what? 40 centimeter what? Cube. Okay. Once we are through with this, you now go to the B part, which is numerical. So, after the titration experiments, the B part will be now from your results, from your results and information provided above. Calculates. In that question, if you can go back, you're already given that the concentration of A is 0.0100. So they will not ask to find concentration of that oxidized agent again. They say calculate concentration of KMNO4 in, okay, rather, this is given FeSO4 in B in mole per dmq. II, concentration of FeSO4 in B in gram per dmq. And then number of Fe2 plus ion produced from volume of solution B pipetted. Maybe you'll be given FeSO4 molar mass is 152, KMNO4 is 158. Okay. Now, from that balance equation, if you go back, you see that from the equation, what's the mole ratio? Mole ratio of A to B is 1. I think is to what? 5. Remember? Let me go back again. Let me write it. Have MnO4 minus plus Fe2 plus Mn2 plus Fe3 plus. During the reaction, the bond holding Mn and O4 break away. Abi? So what's going to pick that oxygen up? Hydrogen what? Ion. It picks it up here, produce H2O, Abi? So how many oxygen is here? Okay, so here we're going to have what? 4 H2O, so we can have what? 8 H plus, Abi? So link these two up now and check how many electrons they produce. How many? 1 ERB. So link these two up and see how many electrons they produce. Well, let's check it. This is 8 minus 1 AB. So here is what? 7. This is what? 2. What's the difference between this side and this side? 5. So have what? 5. So we use this one to multiply this, multiply this, multiply this, multiply this. I think you give me the same thing. So use 5 multiply this, you have what? 5. This, we also have what? 5. So this is balance. So that's where we have the mole ratio of the A is 1, B is what? 5. And then we now use CA, VA over what? CB, VB equals to what? A is what? 1, B is what? 5. Then what do you do here? You substitute. So upon substitution, CA is already given to you as what? 0.0100 times the average volume of the consistent titer used, which is what? 23.40 over what? CB, that's what you are looking for now. This one is what you are looking for, this question, times what? The volume of pipette, which you record as what? 25.00 equals to 1 all over what? 5. Then you cross multiply. On cross multiplying, you have so much. Okay, this times, this give me what? 25 CB is equals to this times this times this. This times this times this. 1.17. That is it? Okay, that's it. Okay, what do you do at this point? We divide both sides by the coefficient of who? CB, which is what? 25 here, 25 here. So that CB alone is what? 0. What? 0.4 what? 6 what? 8 mole per what? DMQ. That is for this one. You can pause the video and check what how we got it. Okay, for the second numerical, for the second part, that is on this concentration of B in gram per DMQ. First of all, now this is going to be your molar concentration of B. So let's write it as one of our parameter. Molar conc of FeSO4 is what now? 0. What? 0.4 what? 68, isn't it? So molar mass of FeSO4 is given. Look at this here, 152. Okay, the mass conc of FeSO4, which is the same thing as concentration of this in gram per DMQ. Let's take it to be what? X. Are you there? Let's take, because that's what we're looking for. That is B in gram per DMQ. So what do you have now? Now have this relation that molar conc is equals to mass conc over what? Molar mass. Students should be familiar with this. Molar mass. So we use these figures, we play with it here. Okay? So what we're going to have here, so here we have 0.0468 is what? So when we have, okay, mass conc is what we're looking for, so it becomes what? X over molar mass, 152. So we cross multiply again. So this is what? X equals to 0.0468 times 152. What is my answer in gram per DMQ? Is what? 7 point what? 11 what? Please keep your answer to 3 significant what? Figure. It says 7.116. 7.114. So you can leave it at 7.11 or 7.11. Let me write it. 7.113 what? 6. Okay, keep your answer like this. 7.11 is okay. 1, 2, 3. They are significant figure. There is no 0 in between here. So 7.11. So what is my units? Don't forget this. You have what? Gram per what? DMQ. Answer. Are you with me? Then the last one. is what? Number of what? Ion 2 produce. I think that can enter here. Let's manage these spots to get it. So we have that from B. This is B. So ionize this B so you can have this man plus this man. So you're not dealing with this. So your concentration should be here. That 1 mole of this decompose, give you 1 mole of this. Okay? So what is the molar conc of this giving? Molar conc of this is already what? 0. So this give me this. 0.0468 gives me what? X. So if you cross multiply, X is the same thing as what? 0.0468. The volume of B is 25, isn't it? So to find the number of mole, I say therefore, number of mole is what? CV over what? Over what? 1,000. N is the number of mole they ask you of ion. So now, concentration of ion is this. So now you substitute. Now say N is now what? 0.0468 times what? What is the volume of pipette? 25 over what? 1,000. Please, this is your answer. Make sure your answer, the unit for mole is mole. Mole is the only unit whose unit is what? Mole. But keep it like this, as units. So what's the answer here? 0.00 what? How many zeros? Make no mistake there. That is the amount of Fe in these pipettes. So what is it? 0.00 what? How many zeros? Is it correct like this? Okay, another one. 1 what? 1 what? I think these numbers are okay. So any other numbers you can throw it away. So if you have 0.00117 like this, or 0.1178, okay, so what's the unit for this? Mole. You can even keep your answer in the standard form as what? Is what? 1.2. Is not it? Times 10 raised to power what? Minus 3. What's the unit there? Mole. I think it's okay. So viewers, you can go through the video again and again so you can understand the principle. The most important thing is to do this table. Make sure that your two readings are consistent. That is not consistent, try to what? Have it ruled like this to signify that that is your rough what? Titration. Since we don't have rough here. Okay? I always tell students not to use rough again. Just first, second, and third. So anyone that is not consistent, what you do to show that this rough titration is what? Slants it with your meter what? With your meter rule. So that is on titration. Okay? Redox titration. So the second question will be on salt analysis.